Imagine a world where objects float in midair, defying gravity. Welcome to the fascinating realm of quantum levitation. A marvel of quantum physics, quantum levitation lets us observe the seemingly impossible. Objects hovering and moving without any support. It's like a magic trick. But the magician here is the intriguing world of quantum mechanics. In this world, superconductors and magnetic fields conspire to create an effect that challenges our everyday understanding of gravity. But this isn't a trick or an illusion. It's a tangible demonstration of the powerful and often puzzling principles governing our universe at the quantum level. A perfect blend of science and wonder, quantum levitation is a journey into a domain where the rules of classical physics take a back seat and quantum phenomena steal the show. So how does this gravity-defying phenomenon work? Let's delve deeper. At the heart of quantum levitation are materials called superconductors. Now you might wonder, what exactly are superconductors? In the simplest terms, superconductors are materials that conduct electricity with zero resistance. You heard it right, zero. This means that an electric current can flow forever in a closed loop without losing any energy. But here's where it gets even more intriguing. When these superconductors are cooled down to extremely low temperatures, they exhibit some pretty unusual properties. One of these is the ability to levitate above a magnetic field. Yes, levitate. This isn't science fiction or magic. It's a very real phenomenon known as quantum levitation. This levitation is made possible by the interaction between the magnetic field and the superconductor. When a superconductor is placed in a magnetic field, it expels the field from its interior, causing it to hover above the magnet. The magic behind this floating act is something called the Meissner effect. The Meissner effect is a phenomenon that makes quantum levitation possible. It's like the secret sauce in our gravity-defying recipe. Now let's break it down. In the realm of superconductors, the Meissner effect comes into play when they're cooled to temperatures below a certain threshold, known as the critical temperature. Once this happens, something quite extraordinary occurs. The superconductor expels all internal magnetic fields. Yes, you heard that right. It gives them the boot, refusing to let them in. Now this isn't just a mild dislike for magnetic fields, it's total expulsion. This is what allows our superconductor to float in midair, seemingly defying gravity. But it isn't magic, it's science. The superconductor and the magnetic field are locked in a delicate dance, maintaining a perfect balance that keeps our superconductor levitating. But there's more to this levitating story. Enter quantum locking. Quantum locking, also known as flux pinning, takes levitation to a whole new level. It's where the magic really happens. When a superconductor is cooled below its critical temperature, it enters a superconducting state, allowing it to expel magnetic fields, a phenomenon we call the Meissner effect. But quantum locking is a step beyond. It involves trapping or pinning magnetic fields in place, creating a stable, locked state. Imagine a spinning top that never falls over no matter how you poke or prod it. That's quantum locking for you. It's a delicate balance of forces, with the superconductor and the magnetic field locked in an intricate dance. It's not just about repelling magnetic fields anymore. It's about creating a relationship between the superconductor and the magnetic field that's so stable, it seems to defy the laws of physics. Now let's see how this eye-catching phenomenon could be used in our daily lives. Imagine traveling in a train that levitates. Sounds like science fiction, right? But this is the tangible promise of quantum levitation. By exploiting the principles of quantum physics, we can create transportation systems that hover above the ground, reducing friction and enhancing efficiency. Take, for example, magnetic levitation or maglev trains. These trains float above their tracks, propelled by powerful superconducting magnets. The magic ingredient? Quantum levitation. It's this phenomenon that allows these trains to skim along at breathtaking speeds, while offering a smoother ride than traditional rail transport. In the future, we might even see quantum levitation used in personal transport devices or in shipping and logistics. The possibilities are truly spellbinding. But it's not just transportation that could benefit from this technology. Quantum levitation could revolutionize numerous industries from manufacturing to space exploration. So while it might seem like we're talking about the stuff of science fiction, the future is closer than you think. Researchers are finding new ways to harness the power of quantum levitation. In laboratories around the world, scientists are pushing the boundaries of what's possible, using this fascinating phenomenon to explore the very fabric of our universe. They're conducting experiments that could one day lead to major breakthroughs in various fields, from material science to quantum computing. You see, quantum levitation isn't just about defying gravity. It's a window into the strange and elusive world of quantum mechanics. A world that's as puzzling as it is intriguing. Researchers are using quantum levitation to study superconductivity, to better understand the Meissner effect, and to delve deeper into the mysteries of quantum locking. These studies could pave the way for more efficient energy systems, faster computers, and revolutionary transportation technologies. But it's not all smooth sailing. Despite these exciting advancements, there are still hurdles to overcome. Quantum levitation, while impressive, is not without its challenges. The phenomenon relies heavily on superconductors, materials that, when cooled to extremely low temperatures, allow electric current to flow without resistance. However, maintaining these chilling conditions outside a lab setting has proven to be a significant hurdle. Moreover, the Meissner effect, which is key to quantum levitation, requires an incredibly strong magnetic field. Creating and controlling such a field on a larger scale is another challenge that scientists grapple with. Additionally, quantum locking, while fascinating, is still a complex process that needs further exploration and understanding. The delicate balance between the superconductor and magnetic field requires precision, making it a tricky phenomenon to master. Lastly, the practical applications of quantum levitation, such as in transportation, face logistical and safety concerns. These issues need to be meticulously addressed before we can witness levitating trains or similar wonders. Yet even with these challenges, quantum levitation continues to captivate us. Nothing illustrates quantum levitation better than seeing it in action. Imagine a disk, seemingly defying the laws of gravity, hovering in midair with no visible means of support. That's quantum levitation for you. It's not magic, it's not an illusion, it's pure science. The disk, made of a superconductor, is locked in a magnetic field suspended above or below a magnet, resisting any change in its position. It can spin, it can move along a track, but it won't fall down. Now picture this, a model train, levitating as it speeds around a track. That's right, a train that doesn't touch the rails thanks to the incredible power of quantum levitation. It's a sight that's as fascinating as it is mind-bending, a testament to the potential of this extraordinary phenomenon. So what does the future hold for quantum levitation? The future of quantum levitation holds endless possibilities. Imagine a world where vehicles float above the ground, eliminating friction and reducing energy consumption. This is not science fiction, but a potential reality made possible by advancements in quantum levitation. While we've touched on applications in transportation like maglev trains, the scope extends beyond this. Quantum levitation could revolutionize industries from logistics to space travel, providing a more efficient and sustainable means of movement. In the realm of scientific research, quantum levitation provides a unique platform for studying fundamental quantum phenomena, opening the door to new discoveries about our universe. However, to realize these possibilities, scientists must overcome significant challenges. Developing superconductors that work at room temperature, for instance, is a key hurdle. But with every challenge comes opportunity. The race is on to harness the full potential of quantum levitation, and the finish line could well be a world transformed. The journey of quantum levitation is just beginning. From science fiction to reality, quantum levitation is a journey into the unknown. We've embarked on quite an adventure today, haven't we? We've delved into the world of superconductors, uncovered the Meissner effect's role in expelling magnetic fields, and even witnessed the mesmerizing phenomenon of quantum locking. We've seen how this captivating science could revolutionize transportation, from maglev trains to potentially even flying vehicles. We've explored the ongoing research in this field and the challenges scientists face in scaling this technology. Yet, despite these challenges, the promise of quantum levitation remains undimmed. Every real-life demonstration of a superconductor locked in midair, defying gravity, is a testament to the wonders of science and the limitless possibilities that lie ahead. So, next time you see something floating in midair, remember, it might just be quantum levitation at work. Until then, keep questioning, keep exploring, and who knows, you might just become part of the next big scientific breakthrough.